Okay, we've got this far. Mathematicians like to call this the difference of two squares, and the way we factorise that is two brackets. The first bracket has got d1 plus d2, and the second bracket has got d1 minus d2. Okay, and the other side I'm going to leave alone, 2ax. Now, to understand this factorisation, well, one thing you can just do is check it. Okay, satisfy it's true by doing a grid d1 plus d2. d1 minus d2, d1 squared up here, d2 squared down here, except it's got a minus on it, because that's a minus d2, and then this is minus d1 times d2, and this is plus d1 times d2, so those terms cancel, so this does indeed multiply out to give that. Okay, so we've now factorised it, so, right now, for that, now all the good stuff starts happening, okay? Let's look at d1 minus d2 first, okay? d1 minus d2, all right, is the long distance from this slit to the first order fringe. Take away the slightly shorter distance from this slit to the first order fringe, and we started by saying that we get the point of maximum intensity with the two waves arriving in phase, okay, when the difference between those path lengths is a whole number of wavelengths, and in this case it's the first order fringe, so this path difference between these two is going to be exactly lambda. So d1, take away d2, this term that's magically appeared out of this bracket, this is just my lambda, that's my wavelength. Okay, that's the difference between the two paths that I need in order to get the waves arriving in phase and forming the bright fringe. Wonderful. Okay, the 2ax I'm going to leave alone, so I'm still going to have equals 2ax. Okay, I've just got to deal with this. Now, d1 plus d2. Now I'm going to do an approximation. Looking at the diagram, if we've just got these two slits, if you've seen this experiment, then you will know the two slits have to be very close together, and that the fringes you get some distance away are really also quite close together. Certainly a lot smaller distances involved at this end and this end compared with this distance between them, which means that these angles here that I've drawn as quite appreciable angles, okay, are really tiny, and d1 and d2 in percentage terms will be hardly any different at all from d. Remember, the difference in length of d1 and d2 is just the one wavelength of light. It's a tiny number. So all the vertical distances here are tiny compared with the horizontal distances. So when I've got d1 and d2 left in my formula, I can approximate them each as d. When they're being added together, the difference is another matter, because that would have become 0, and lambda is indeed quite close to 0. But d1 plus d2, okay, is a big distance, and it's almost exactly equal to twice the distance between the slits and the screen, because d1 is almost the same as lambda, and d2 is almost the same as lambda. So that's where my 2d has come from. So now I've got an equation. It's got a 2 on both sides, so I can divide both sides by 2. So the 2's are just going to disappear. And my lambda, okay, is going to equal a times x over d, which is the formula that you can look up in your data booklet and apply. Okay, so we've seen where that formula comes from, and that's the end of this little sequence. Don't worry, you won't have to do this proof, but at least you know that this formula is not just magic, it does come from some proper maths.